Today we will study double differentiation first, and then we'll go for second application of derivative of dy by dx. Let's see what double differentiation means. Suppose you have a function y equal to f of x. Then if you differentiate it once, then you get dy by dx, which is simply differentiation of the expression in x. Now, if you differentiate it one more time, so you differentiate the expression for dy by dx in x, then it is called double differentiation and is represented by d2y by dx2. So double differentiation is simply d2y by dx2. This is the representation, and it is nothing but d by dx of dy by dx. For example, if we have y is equal to sin x, so first derivative or first differentiation of y with respect to x will be d by dx of sin x, which is basically cos x. Now, then the double derivative of y with respect to x will mean d by dx of dy by dx, and you can see here this dy by dx is nothing but cos x. See here, dy by dx is cos x. So we have substituted dy by dx with cos x, and the result will follow. So the double derivative of sin x would be minus differentiation of cos x, which is minus sin x. Let's do another example. Let's suppose y is x cubed plus 4x plus 3. Then dy by dx is simply dy by dx of this term x cubed plus 4x plus 3. So first derivative you are already familiar with. This will become 3x square. Differentiation of first term will be 3x square. Differentiation of second term will be 4 into d by dx of x, which is 4. Differentiation of third term will be 0 because it's constant. Now, d2y by dx2 will mean differentiating this result once more. Then you can simply directly write this is equal to this, where this term is dy by dx. So you will get 6x, and differentiation of second term will be 0. So the first derivative of this expression is 3x square plus 4, and second derivative is 6x. We'll continue with our application of derivatives. We have seen the first application of derivative, which is rate measurement, and this time we are going with second application of derivative, or dy by dx, goes by the name of maxima or minima of a function y equal to fx. Before that, I wish to remind you of some of the findings that we had, that given a curve y equal to fx, the slope of the tangent at any point, this is dy by, the slope of this line is or tangent at x is nothing but dy by dx at x. Let's try to extract some more information. And now we have three lines: line number 1, line number 2, and line number 3. You can quite clearly see slope of the tangent L1 is positive. That means dy by dx at a is positive, is greater than 0 because slope of L1 is positive. Because it will make acute angle with the positive x-axis. Similarly, you can see the slope of tangent at B is almost parallel to x-axis. So dy by dx at B is 0 because slope of L2 is 0 because it's parallel to x-axis. The angle made with the x-axis is 0. The slope of the tangent at C, you can see it makes an obtuse angle with the positive x-axis and tan theta of that angle will be negative. So dy by dx at C is negative because slope of line L3 is negative. There is a very important point to note here that you can see between A to B, the part of the curve, y is increasing with x. With B to C, y is decreasing with x. So the value of the function is some sort of increasing here. And the value of the function around C is decreasing with x. So we can quite clearly note that whenever y increases with x, the slope of tangent in that region is positive, like this. Whenever y goes on decreases with x, as x increases, y decreases, then the slope of the tangent is negative, as in case with C. And whenever the slope becomes parallel to x-axis, obviously the slope is equal to 0. Note a very important point here that if y increases with x, as x increases, then obviously dy by dx has to be positive. If y decreases as x increases and vice versa, then dy by dx surely must be negative because the slope of the tangent would make an obtuse angle with positive x-axis in this case. Now consider a curve y equal to fx here, which changes with x in this fashion. Sometimes it increases with x, and then at others it decreases with x. It again then increases, decreases, and so on. So y is increasing or decreasing with x in the region. Then you can see that in this region, y attains a maximum value. It increases, and then it starts decreasing. So at certain point here in this region, y attains a maximum value locally. Then you can see here, this region over here, y decreases with x and then increases. So obviously it attains a minimum value here. Same goes here. In this region, y again starts to increase and then decrease. So in this locality also, y attains a maximum value. Same goes here, it attains a minimum value here, then attains a maximum value here. So there are points in the region at which y attains a maximum or minimum value locally. Those points are called points of maxima and minima. Example, in this case, the value of x, let's say this is x1, at which y attains a local maximum value. That means the value at x1 is relatively higher than its locality. It's called local maxima or simply maxima. the value of x at which the y attains a local minimum value is called points of minima. And we can mark all maximas and minimas here. We have a minima here, x4. We have a maxima here, x5. So, if this is a general curve, then we can see there are many numbers of maxima and minima in this curve, namely x1, x2, x3, x4, x5, simply because y attains a relatively higher or lower value in the region. Our target today is, given the function y equal to fx, not the graph, okay, given the function y equal to fx, can we find x1, x2, x3, x4, x5 points at which this function attains a local maxima or minima? Which are the points of maxima and minima? So we should start observing the graph to develop a mathematical model that will give you the values of maximas and minima points. So if you look at the graph closely, you can see at all maxima and minima points. Now look at the slope of the tangents at maxima and minima. Looking at the slopes of the tangent at maxima and minima, at x1, the maxima you can see the slope of the tangent to the curve y equal to fx. The tangent is really parallel to x-axis and the slope of the tangent is 0. Now at this minimum, x3, you can see the slope of the tangent will be 0 because the tangent is parallel to x-axis. Angle made with the x-axis is still 0. Same goes with x3 and x4 and x5. At all maxima, which are highlighted by green, the tangent is really parallel to x-axis and the slope of the tangent is 0. Same goes with all minima points. The slope of the tangent at minima x2 and x4 is also 0. So, given a curve y equal to fx, we have seen at all maxima and minima points, the slope of the tangent must be 0, whether it is maxima or minima. So we can write a mathematical condition here that maxima or minima will have dy by dx equal to 0, which is an equation, and roots of which will be all those points x1, x2 and so on, which are either maxima or minimum points. So at all maxima and minima point, we have dy by dx equal to 0, which is a very important mathematical condition to obtain those points from the equation y equal to fx. You take the first derivative or differentiate y with respect to x. If you equate it to 0, that equation gives you the roots at which maxima and minima points are obtained. So far we have obtained that given a curve at all maxima and minima points, the slope of the tangent is 0 and we have obtained those points x1, x2, x3. They are combinedly known as extrema points or maxima or minima. So the equation dy by dx will give you x1, x2, x3 and other points at which dy by dx is 0 or the slope of the tangent is 0 or there is a maxima or minima. But now we have to devise another mathematical tool to figure out whether there will be a maxima or minima at In order to do that, we must clearly make a distinction between maxima and minima. For example, there is a maxima at x1 and there is a minima at x2. So we have to look for the difference between x1 and x2. What happens to the curve at x1 and what happens to the curve at x2 in mathematical sense. Now, in order to understand the difference between a maxima and minima in true mathematical sense, we must go in details what happens around maxima and what happens around a minima. So if we can go close to a maximum, then you can see the slope of the tangent before maxima. So this is your maxima. Let's say that is x1, maxima. You can see the slope of the tangent to the curve is positive because y is increasing with respect to x. The slope at maximum is 0 because the tangent is parallel to x-axis. And after x max, the slope of the tangent is negative. What does that mean is around x max, so we have around x max, we have a trend like dy by dx is going from positive 0 negative. That means dy by dx is decreasing. So dy by dx decreases as x increases. As x increases, dy by dx decreases. Let's try to look around a minimum. So let's see what happens around a minimum. You can quite clearly see that this point is a minimum point. Let's call it x mean. So around minimum point, the slope of the tangent before minimum, y is decreasing, the slope of the tangent is negative. At minimum, it is 0 because dy by dx is tangent of the slope of the tangent, which is parallel to x-axis obviously. And after the minima, as x increases, the slope becomes positive or y starts increasing with x. So what happens to dy by dx? It goes from negative 0 to positive. That means dy by dx around minima is increasing unlike what happened at maxima. You can see here that dy by dx is increasing as x increases around a minima. So we have seen dy by dx decreases at a maximum and dy by dx increases at a minimum. So if dy by dx increases with x, which happens around a minimum, and we have dy by dx decreases when x increases around a maximum. Let's try to put this condition mathematically. If y increases with x, we say dy by dx is positive. So here, you can write the analogy here. Y increases with x, then we write dy by dx is greater than 0. When y decreases with x, we write dy by dx less than 0. So what happens when dy by dx increases with x, then dy by dx of dy by dx. So this is your y now. It must be greater than 0. If dy by dx increases with x, its derivative should be greater than 0. So we can write the result like this, that around minima, this is nothing but double derivative of y with respect to x should be greater than 0 at minima. Same goes with this. If dy by dx decreases with x, then dy dx of dy by dx should be less than 0. So it follows that dy dx of dy by dx, its derivative should be less than 0. What does that mean is double derivative of y with respect to x should be less than 0 at a maxima. Now let's try to summarize our understanding in a mathematical model to find maximas and minimas of a function. So given a function y equal to fx, what you can do is find dy by dx, let's say that is f dash x, which is nothing but the differentiation of the expression fx. Then this is step number 1. Step number 2 is we'll identify at maxima or minima slope of the tangent should be 0. That means dy by dx must be equal to 0. Solving this equation, let's say roots are x1, x2 and so on. Then we will move to the third step to identify whether x1 or x2 or x3 is a maxima point or a minima point. For that we have understood that the double derivative should be greater than 0 at minima and double derivative should be less than 0 at maxima. Simply because at maxima the slope is positive first, then it goes 0 and then it goes negative. So the slope is decreasing, that implies its derivative should be less than 0. At minima, before minima you can see the slope is negative, goes to 0 and then goes to positive. That means dy by dx is increasing, that implies its derivative should be greater than 0 at minima. So we call it double derivative test. So we have in the next step, we'll do double derivative test to classify maxima and minima. So if at x1 d2y by dx2 or double derivative of y with respect to x is greater than 0, that implies x1 is a minima. If at x1 d2y by dx2 is less than 0, that implies x1 is a maxima. So these are the steps to find out maximas and minimas of a function.